Our second chapter is all about probability. We're going to start off in this video with a discussion of some somewhat basic probability, including combinatorics and counting, and go over a couple of the homework problems. And then in the next video, we'll talk about a little bit more complicated probability and some probability rules. One of the problems with this chapter is that sometimes questions involving probability can be very simple, and that kind of fools us into thinking that we're always going to be able to do the problems intuitively. For example, if a fair coin is about to be tossed and we're asked what is the probability that lands heads face up, most people would answer 50% or 1/2. In this case, our intuition is correct. There's two things that can happen, and one of them is heads, so the probability of heads is 1/2. And our intuition also usually tells us that the outcome should be equally likely. If someone were to say that they have a 50% chance of winning the lottery because there's only two things that can happen, either they win or they don't, most of us realize that that's kind of ridiculous because those two things, winning and not winning, are not equally likely. Often probability classes at this point get into a discussion about sample space and other technical terminology, but we're going to just start off with some simple notation. So basic probability formula. If we want to know the probability of a certain outcome, we will call it A, capital letter A. The probability of A, or the probability that A happens, is the number of ways event A can happen, divided the total number of things that can happen, or the total number of outcomes that can happen. So this ratio gives us a probability. In the case of our heads example, it would be the number of ways that heads can happen divided by the total number of outcomes that can happen when tossing a fair coin. You can write it out in words. The words heads, you can abbreviate heads with the letter H. You could have a statement that says something like, let A equals heads, and then write A. You'll notice that in a lot of different probability problems, the capital letters A, B, and C tend to get used a lot in much the same way that X, Y, and Z get used a lot in algebra-based classes. So anyways, we would say that the probability of heads is 1/2 because there's two total outcomes that could happen. One of them is heads, so that probability is 1/2 or 0.5, or I suppose you could say 50%. Probability is often expressed as a fraction, sometimes as a percentage, but I prefer decimals going to 4 or 5 places as needed. So here's a little bit more tricky problem. Suppose we toss the coin 3 times and we want to know the probability of getting exactly 2 heads. So we need to know the number of ways that 2 heads can happen, and we need to know the total number of things that can happen. So in this case, there's a few more possibilities, but it's still a small enough number of possibilities that we can list them all out. Here's all the things that I believe can happen when you toss a coin 3 times. Anywhere from all 3 heads to all 3 tails. And I believe if I've listed them all, there's 8 different things that can happen. So there's 8 different things that can happen, and all the outcomes are equally likely if it's a fair coin. And it looks like we've got 1, 2, 3 of those outcomes that result in exactly 2 heads. Therefore, the probability of exactly 2 heads is 3/8 or 0.375. This is, by the way, this is going to come up in another problem, but we could have predicted there was 8 things that could happen because 2 possible outcomes on each toss, and 2 times 2 times 2 is 8. So in this realm of probability, there's a lot done with combinatorics, counting the total number of things that can happen for the denominator, and then counting the total number of ways that the event can happen for the numerator. However, sometimes one or both of those, the numerator or the denominator, can be difficult to count or enumerate. Here's another example. Suppose I toss a fair coin 10 times. What's the probability that somewhere in those 10 flips, I will see 3 heads in a row? In this case, if you followed what I talked about up here, the total number of outcomes that can happen is easy. 2 to the 10th power is 1024. The numerator is a little bit tricky because it's hard to know just off of the top of your head how many different ways that heads, heads, heads can happen. By the way, it can happen in hundreds of different ways. And sometimes you could get heads, heads, heads in more than one place in the 10 tosses, or you could get 4 heads in a row or 5 heads in a row, which also counts as seeing heads, heads, heads. And if I wanted to take the time to list all 1024 things that could happen, then I could go through that list and count how many of them have heads, heads, heads. But it's much quicker, I think, to run a simulation. I'm going to do the simulation a couple different ways. I think computer science people might appreciate this. So I'm going to do an if statement with a rand statement to randomly put H or T to represent heads or tails. And then I'm just going to copy that 10 times and maybe change the width of these columns. Okay, so there I have my string of 10 heads and tails. I'm going to turn that literally into a 10-character string. Okay, and then I'm going to search for, by the way, every time I click on something or type something, it re-randomizes. I'm going to search within, I'm going to search for HHH within that text. And if it finds it, it returns a number, which is the location where the HHH begins. Here the HHH begins in position 5. And I get kind of an error message if it does not find HHH. So what I'm going to say is, if this is numeric, then return a 1, meaning I found HHH, otherwise return a 0. Not is numeric, is number. So 0 means that we did not find HHH. 1 means that we did find HHH. Just going to do this a couple more times to convince myself that the simulation is working. Okay, so now all I have to do is copy this maybe like a million times. Computer might freeze up here, so I might lose my video for a second. I've got a little progress bar down here at the bottom, which is moving fairly quickly, so that's a little bit promising. And even when the progress bar is done, it's going to pause for a few seconds just to update the screen. It might even give me that old not responding error for a second. Here we go. So that just pasted the exact same thing. Now the randomization has to occur. like re-randomizing this 1 million times. So the paste happened, it's calculating, and it's done. So now I want to count how many times we saw HHH. Let me just do the sum of L1 through L1 million. And again, I type something so it re-randomizes, and then I can do that number divided by 1 million, and that'll give me my probability. So it looks like the probability is about 508. Sometimes I get 507 point something, but usually even when I get 5, by the way, every time I press a key, I'm redoing the whole randomization. So it looks to me like the probability is around 507 or 508. When I did my notes, it turned out to be this. So basically, in this case, instead of going through all the 1,024 things that could happen and counting how many of those 1,024 things result in HHH, that would be referred to as the classical approach. Instead, I'm doing what's called a relative frequency approach. I'm simulating this 1 million times, and I'm looking at how many of my 1 million simulations result in HHH somewhere. And so this is a pretty close approximation of the probability. So this gives me an approximation of the probability using relative frequency. And sometimes this is done via simulation, but other times it's done using real life data. Like if a life insurance company wants to know the probability that I will live until 70, they will look at past data and they will look at all people my age and see how many of those people make it to age 70 and then form a fraction like this. I wanted to show one more thing. So that's the simulation in Excel. You're not going to have to do said simulation, but I also have another simulation over here in CodeHS where I did this in Java. I know this is really small print, but I did this in Java 10 million times, and I'm getting a probability of 5078. So I'm pretty convinced that the probability of seeing heads, heads, heads is about 0.508. Okay? Okay, so now some different ways of counting the numerator or the denominator. First of all, let's talk about factorial. In mathematics, factorial, which appears like an exclamation mark, not to be confused with the bang in computer science that means not, this means recursive multiplication. For example, 5 factorial is 5 times 4 times 3 times 2 times 1, and so on. It is a little bit strange that 0 factorial equals 1, but that's just something that you have to live with. If you really want to be bothered by 0 factorial being 1, could kind of blow your mind a little bit by doing 0.5 factorial. Check this out. 0.5 factorial is going to be a little bit surprising. It's some long, ugly decimal number. And what's even more surprising about this long, ugly decimal number is that if you square it and you multiply by 4, you get pi. So yes, somehow pi is involved in factorial when the number that we're doing factorial is not an integer. But for the purposes of what we're doing in this class, the old school standard definition of factorial is going to be fine. The main thing we need factorial for is for its use in 2 different formulas. First of all, permutations. Suppose we have the letters A, B, C, D, E, and we want to choose 2 of those, and suppose that order matters. There's 20 ways that this can be done. Notice I've put up here we're choosing two letters without replacement, meaning, so I'm not going to count the possibility of an A followed by an A. So I think I've got all these listed. The A with every other possible letter, the B with every other possible letter, and so on. And I believe that there's 20 ways that this can be done. And again, notice I'm counting A, B, and BA as separate permutations. If this problem were significantly larger, we would not be able to list all these things. So we need a formula. And here's the formula involving factorial. The permutation of n items taken r at a time is n factorial over n minus r factorial. In the example we just did, n would be 5 and r would be 2. And if we plug the 5 and the 2 in place of n and r, we get 20. So we don't really have to list all of those to know that it's 20. We have a function on our calculator, and I'll show you the function on my calculator, math probability permutations. So sometimes the notation is to have the n in front of the p and the r after the p. And sometimes they're both after the p. But anyways, we have a function built in our calculator that will figure out permutations for us. And most scientific calculators will have permutations somewhere built in. It's kind of interesting to notice that if you were to write out these factorials in problems involving permutations, there's always a lot of canceling out that goes on. And notice after this canceling out, all we're left with is 5 times 4, which is 20. So as I was mentioning, sometimes the notation would have the 5 in front of the p, and sometimes this generic written notation instead of the r would use the letter k. Now, very closely related to permutations is combinations. The only difference is with combinations, the order does not matter. So with combinations, we're not going to list A, B, and BA, because we're going to treat that as if they're the same. So I've got A listed with every letter, but I'm not going to list the B with the A because I already have the B with the A over here. And if I follow that routine for listing all the combinations, you see that there's only 10 ways that we can choose 2 of the letters if order doesn't matter. And again, for larger problems, we have a formula that will do this for us. Very similar notation, except for the capital letter C. And we have an extra term in the denominator. We have an r factorial term in the denominator. So in our example with n equals 5 and r equals 2, we plug those in and we have this. But of course, our calculator, if we go math and then probability, the third item down is combinations. Or if you have a different calculator, I'm sure you can find it on your scientific calculator. 5 items taken 2 at a time. And there's 10 ways that that can happen. So I opened this up with a discussion about factorial, but if we're using a calculator function for permutations and combinations, we really probably don't even have to know about the factorial. So here's just another display of both of those on the graphing calculator. Something else that's really interesting to note is that, and this could get into a really long-winded conversation, but it's kind of interesting to know that the combination numbers are in Pascal's triangle. So if you do 5, choose 5, and I didn't type that up in the notes, but sometimes with combinations, in particular with combinations, this notation is read out loud as 5, choose 5. So 5 items and we're selecting 5 of them. There's one way that can happen. 5 items and we're selecting 4 of them. There's 5 ways that can happen. And then 10, and then 10, and then 5, and then 1. That's just one row of Pascal's triangle. So there's kind of an interesting connection between combinations and Pascal's triangle and something called the binomial theorem that some people learn about in advanced algebra. Anyways, one other thing here is that sometimes a student not well versed in statistical terminology would look at this list and they would say, oh, that's all the combinations of the letters A, B, C, D, and E. But there's different terminology for this list and this list. So a person who is well versed in statistical terminology would recognize that this is all the permutations of A, B, C, D, E, taken 2 letters at a time, while this is all the combinations of the letters A, B, C, D, E, taken 2 at a time. Also, beware of situations, and we'll see one of these on the homework, beware of situations where you're sampling with replacement, so that the letter A would be possible twice. That would not fall into the category of either permutations or combinations. We'll talk about that in a moment. So now that we know about permutations and combinations, we can find some probabilities of more interesting problems. For example, the original California lottery had 49 numbers, from which 6 were chosen. In this situation, the order does not matter as long as the 6 numbers that I picked on my lottery ticket are selected. It doesn't matter if they're selected in order or not. So, if a person buys a single lottery ticket, what is the probability of winning? Well, there's only one way the numbers can be chosen that matches this person's ticket. The denominator would be the combination of 49 items chosen 6 at a time, or sometimes that would be referred to as 49 choose 6. And if I bounce back to the calculator, 49 items, choose 6 of them, there's 13 million, almost 14 million ways that can happen. So with one lottery ticket, this is back when the California lottery started, with one lottery ticket, your probability of winning would be 1 out of 14 million, which is a really, really tiny decimal number. So let's look at some of the homework problems and how we could use permutations on this. So this first problem is going to use our probability formula, but it's not going to use combinations or permutations. This is kind of dated also because it's dating back to 2006. How many domain names, web domain names, could you make just consisting of 2 letters in sequence? So in this case, it is possible to use the letter AA as a domain name, like aa.com. So there's 26 letters that could be the first letter and 26 letters that could be the second letter. So there's 676 different 2-letter combinations that could be chosen as domain names. And they go through this several different scenarios involving this. And they end up with how many could you do with 4 letters if you're able to use letters and digits. So if I can use letters, that's 26 things. And if I can use digits, that's another 10 things. So there's 36 things that could be used, 36 different symbols, and we're doing 4 of them at a time. So that's going to be 36 times 36 times 36 times 36, or you could say 36 to the 4th power, of course. So 16 million roughly. That's where this number is coming from. And then they say, as of a certain date, this many of those 4-character sequences, using letters or digits, had not been claimed. So I'm going to subtract 95,875, which means 15 million and change have been claimed. If a 4-character name is randomly selected, what's the probability that it's already owned? Well, 15 million of them are already owned. So if I divide that by 16,796,000, well, that's not 16 million, 1,676,616, I get that there's about a 94% chance that the randomly selected name has already been chosen. So 9429 or 943, and that's what we're seeing as the answer right there. So that problem is just using some basic multiplication, and it's making use of this initial probability formula that we had, the number of ways that event A can happen and the total number of outcomes. Okay, so hopefully I'm not giving away any answers here because you're all going to get slightly different randomization. Someone's holding a dinner party and they have 7 bottles of Zin, 11 bottles of Zinfandel, 7 Merlot, and 9 Cabernet. If the person serves 3 bottles of Zinfandel and order is important, how many ways are there to do that? Well, this says that I have 11 bottles of Zinfandel, so that would be math, probability, combinations. Let's try that again. Math, probability, combinations, 11 bottles, and I'm choosing 3. Oh, wait a second. They said and order is important, so I don't want combinations, I want permutations. Probability permutations, 11 items, and I'm selecting 3. There's 990 ways that can happen. There's that answer right there. If 6 bottles of wine are randomly selected from the 27, how many ways are there to do this? And this one doesn't say order is important, so I'm going to assume that this one is combinations. So they gave us a total of 27 bottles of wine. And we're choosing 6. Fix this here, 27, and we're choosing or selecting 6. There's 296,000 ways that could happen. Now, the next part says, if 6 bottles are randomly selected, how many ways are there to obtain 2 bottles of each variety? So this is a little bit more tricky. First of all, I want to get 2 Zinfandel. So to get 2 Zinfandel, that means of the 11 bottles of Zinfandel, I need to select 2. So of the 11 bottles of Zinfandel, I need to choose 2. Oops, let's try that again. So there's 55 ways that can happen. And then of the 7 bottles of Merlot, I want to choose 2. "21 ways that can happen. And then of the 9 bottles of Cabernet, I want to choose 2. So I'm choosing 2 of each type. Not just 6 completely at random, but 2 at each type. So there's 55 ways to choose 2 of the Zinfandels. There's 21 ways to choose 2 of the Merlots. And there's 36 ways to choose 2 of the Cabernets. So there's 41,000 ways to pick 2 of each wine. So there's that 41,000. And then they want us to turn this into a probability. There's 296,000 ways that we can select 6 bottles of wine from the 27. And of those 296,000 ways, 41,000 result in 2 of each variety. So if I do that 41,000 divided by 296,010, that gives me a probability of about 0.14. So the probability of that happening is about 0.14. And this problem is very similar, and this problem is very similar. So this problem is very similar. So all of those first several problems are going to deal with combinations and using our very basic probability fraction, the number of ways something can happen divided by the total number of things that can happen. So that's going to be it for this part of the lecture on probability, and stay tuned for another video on some more intricate ways of calculating probability.